Hello students and welcome to lesson 3 of our geometry unit. This lesson is titled Similarity Based on Transformations. In this lesson we're going to learn about one more transformation called a dilation, and we're going to learn about the result of a dilation called a similar figure. So our essential questions are: what are dilations, which are also known as similar figures? What properties do dilations or similar figures have? How can I decide if two figures are similar? And if two figures are similar, how can I find a missing dimension? So, in our last lesson, we learned about congruent figures. We learned that congruent figures have the same shape and the same size. So, we also learned that we can transform them in 3 different ways. We can translate, rotate, or reflect them, and the shape and size will remain the same. The congruency will be preserved. We are going to learn about one more type of transformation today, and that is a dilation. A dilation is a change to a shape's size. A dilation creates an enlarged or reduced version of the shape, and a synonym for a dilation is called a similar figure. Similar figures have two main properties. Like congruent figures, they are the same shape, but different from congruent figures are similar figures are a different size. The same shape is created by having angles that are congruent. So anytime you are in question whether something is a similar figure or not, check the angles, because corresponding angles must be congruent, meaning have the same measure. To be a different size, their side lengths cannot be the same length. However, their corresponding side lengths must form equivalent ratios. Now, in the past, we have learned about equivalent ratios. We've learned two skills. One, how do we decide if two ratios are equivalent? And two, how can we use that to figure out a missing dimension? So we're going to warm up with some review questions here. So on the question on the left, we are going to decide, are these two ratios equivalent? Now remember, if two ratios are equivalent, then they have to have equal cross products. So you're asking yourself, do they have equal cross products? So does 3 times 30, which is 90, equal 10 times 9, which is 90? And the answer is yes. So if two ratios have equal cross products, then the ratios are equivalent. So these two ratios are equivalent. Now, knowing that can help us find a missing value, because if we know that they are equivalent, then we can use cross products to write a one-step equation. So for example, 3 times x is 3x. 7.5 times 7, so 7.5 times 7, 7 times 5 is 35, 7 times 7 is 49, and 3 more is 52. One decimal place, so we get 52.5. Now, if you remember, if two ratios are equivalent, then their cross products are equal. And if you look at what we've wrote a one-step equation, an equation that takes one step to solve. We have 3 times x. Since we want to know what just x is, divide each side by 3, because 3 divided by 3 is 1. Then we'll know what 1x is. Divide this side by 3. 3 goes into 5 one time, which is 3. There's 2 left over. Bring down the 2. 3 goes into 22 7 times, which is 21. 1 left over. Bring down the 5. 3 goes into 15 5 times, which is 15. There's nothing left over and nothing more to bring down, so this is our final answer. All we need to do is bring a decimal straight up, and we get 17.5. So the value of the missing amount is 17.5. This is the only number that we could substitute in for x and make these ratios equivalent. Okay, now that we have reviewed what it looks like to be equivalent and how to test it, we are going to practice deciding whether shapes are similar or not. Now, when we ask that question, what we're really asking is, do they have the same angles? And do they have the same ratios of side lengths? So if you look at these two examples, these two triangles, you can see that this is about a 45-degree angle. This is about a 45-degree angle. We have our 90-degree angles, and we have, again, about 45-degree angles. Now, when you are testing the same angles, you don't have to be completely particular. Do they look the same shape? Obviously, if I had a triangle that looked like this, you would see this has to have different angles than this one. So, ballpark, do they have the same angles? Yes. Now, let's check the ratios of sides. Well, you know that a ratio compares two amounts. In this case, we can compare the base and the height of each triangle by counting the units it has lying on the coordinate plane. So it has 1, 2, 3, 4, 5, 6 units as its base, and 1, 2, 3, 4, 5, 6, 7, 8 units height. Now be sure that you label what your ratio is comparing so that you create a similar ratio here. So we're going to make a base to height ratio. So our base was 6 units and our height was 8 units. And I like to just label my ratio so now I know which triangle I got it from. So this was the big triangle. Alright, now let's write a ratio similar, base to height, for the smaller triangle. Its width is 1, 2, 3, so we get 3 units. 1, 2, 3, 4 high, which is 4 units. So for the small triangle, we got 3 units over 4 units. Now, you do have two options for how you decide if they are equal ratios or not. You could cross multiply. 6 times 4 is 24. 3 times 8 is 24. And you see it has equal cross products. So these would be equivalent. These two shapes would be similar. Okay. Your other option is to reduce the ratio. See how this one's 3 to 4? 3 and 4 have no common factors. If you look at 8 and 6 and 8, they can both reduce by 2 to get 3 units to 4 units. And you can look and say, oh, well, if you look, the two ratios are equivalent, so that means they are similar. That's how you would reduce it, and this is what it would look like if you would use your cross products. 6 times 4 is 24. 3 times 8 is 24. So they're equal in value. That means that these shapes are similar. Let's try another example. Are these two shapes similar? In other words, do they have the same angles, and are they the same ratios of sides? Well, if you look, they look fairly similar to each other. So we're going to say they have the same angles. Now let's look at their ratios of sides. Let's once again write a base to height ratio because in this lesson you do not yet know how to calculate this diagonal. That's what you will learn in lesson 4. You only know how to count the units up and to the left. So we can see that this one has a height of 2 units and a width of 4 units. The bigger triangle has 1, 2, 3, 4, 5, 6 units, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units long. So if you write your ratio for the small triangle, the one we did first, our base was 4 units, our height was 2 units. And you could have that backwards if you did height to base, just got to be consistent. And let's do that to the large triangle. Base was 10 units, height was 6 units. Now let's cross multiply this one. 4 times 6 is 24. 10 times 2 is 20. These cross products are not equal, so that means that these two shapes are not similar. They do not have the same ratios of side lengths. Are these two shapes similar? Do they have the same angles and the same ratios of side lengths? Now, if you look at this example, you can see that they are similar to each other because they both have right angles. However, one has been rotated, so when we go to write our ratios, we're going to have to be careful that we're actually comparing the same parts of the triangle. So for example, here is the shortest side. It is the base in this case. But if you look at this triangle, the longest side is considered the base. So instead of calling it the base and the height, we may want to say length and width, or short side and long side, something to be a little more specific. So we're going to say, okay, this is 2 units, and let's call that the short side. And our height, in this case, 1, 2, 3, 4, 5 is 5 units. Let's just put that's the long side. On our other rectangle, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 and a half. So we have 9.5 units. And that will be our long side. And we have 1, 2, 3 units as our short side. So let's write our similar ratios. Let's do short side to long side. Okay. Our short side on the smaller rectangle is 2 units. And on our long side is 5 units. On our larger triangle, our larger rectangle, our short side is 3 units. And our longer side is 9.5 units. Okay. Now, let's cross multiply to see if these are equal. 2 times 9.5. Well, we know that 2 times 9 is 18, and 2 times a half is 1. So what is 18 plus 1? 19. If you didn't know that, you could do it on the side of paper. 3 times 5 is 15. 15 does not equal 19. So do they have the same ratios of side lengths? No. Are they similar? No. They are not similar figures. They are both rectangles, but their mathematical properties do not align with the qualifications for being similar. I'm going to pause there for a minute, and in part 2, I will show you how to find the missing dimension in similar figures.